Hello. Hi, everybody. Uh, Good to see you all out there. Welcome to Chemistry 40S, and we're back at it. Equilibrium is almost done, so this is very exciting. Hopefully, you're finding it thrilling. I think we're probably a little short on assignments. I think we'll get an equilibrium assignment out there uh, later today. So hopefully, life is going okay at home, and you're staying safe, washing your hands, all that sort of thing. All right, let's start with a quick little recap of yesterday by doing this question here, and then we will carry forward into the next part. So for this chemical equation, which is methane plus water in the gas phase, changing into carbon dioxide or carbon monoxide plus hydrogen gas, we need to predict the effect of the equilibrium position that results from an increase in temperature. So when we increase the temperature, we can think that we have done an increase here of the energy. This is an endothermic reaction. And so this increase will result in, I'm trying to do this tip to tail here. So tip of the arrow to the tail of the other arrow, and that will draw us this arrow here. So we're going to end up touching that arrow, and that means that we're going to the right. So shift to right. Feel free to give me any comments on whether you like this tip-to-tail idea or if you like a different approach better. We can do the balance approach. You are decreasing the temperature. So let's maybe, what if we do arrows down like this, and if the arrow is down, we have to go from the tip to tail this way. No, that wouldn't make sense. This way? Kind of works. Okay. It's not quite as clean. I was hoping for something like that to work out. You could think about it that, I have thought about it like there's a little well here. So you're saying there's a little well, so the water will fall down. And in the previous one, we had a little hill, so the water would fall that way. So we have to fill the well, and so maybe, oh yeah, what if we do, uh, hmm, tip to tail would have been nice, eh? I wanted to kind of draw something like this. And so what would that look like? Kind of like that. So we know that we need to bring the temperature back up. And so maybe something like that. I don't know. But if you have a decrease in temperature, then that means that your temperature is down. And so you need to fill in the little gap. Um, maybe we'll use like a diving board. So this is a shift to the left. If we decrease the pressure, decreasing the pressure, so we're removing gas from the system or removing pressure from the system, that means that all the concentrations are decreasing, right? So we are going to get, maybe I'm going to write out decreased pressure equals all concentrations decreased. So if we look at it this way, we have CH4, H2O, and then CO plus 3H2. I kind of think about it in my mind, what I'm doing is I'm kind of going like, okay, I got 1, 2 arrows here, and I get 1, 2, 3, 4 arrows here. So overall, which one is lower? And we see that the lowest one is going to be, if we kind of stack them like this, we can see which one is in most need of filling? Well, notice that the amount of drop here is much higher on the right than it is on the left. So we are going to have to fill that space. So we're going to follow the arrow towards the direction of, well, it kind of works to point it at the tip, doesn't it? Tip the tail. Yeah, tip the tail pointed at that really giant arrow going down, and we need to follow that arrow, follow that big force, and fill it up. So that's so we're gonna move. We're gonna shift right. The right side has the larger change. Okay, decreasing the volume of the container means that you're going to be increasing all concentrations. So we can really just grab this and let's see if I can do like a flip. And we can do the same thing with this other one. Okay. And I'm just going to get in, erase that. So following this logic, we would start from the highest point here and move to the lowest point, and that would be to move down to this arrow, starting from tip to tail. Ah, yeah, okay, let's do it that way. So if we always start from the arrow that is the highest, then sometimes that arrow is going to be the equilibrium arrow, sometimes that arrow is going to be the arrow you put beside your letter, and then go tip to tail again. So tip to tail from our point up here, we're going to go all the way down to this bottom arrow that is pointing this way. We can't go to the other one because it's backwards. And so that will tell us that we are moving our matter to the left. So move that matter to the left because you got way too much on the right. So it's going to be shift left. Adding a solid drying agent such as calcium chloride, which reacts with hydrogen with water. So this is a weird one to sort of wrap your head around. What is that process going to be? What is a solid drying agent like calcium chloride reacting with the water? Why would that have an effect? Well, if it reacts with water, what does it do to the concentration of water? That's right. It must be removing water from the system. So in our CH4 plus H2O goes this way, CO plus 3H2. We are dropping the amount of water, and we're going to go from the arrow that is highest on the vertical scale to the arrow that is the lowest. So here, this arrow is higher. So this arrow is going to follow the arrow and follow it downwards. So we are going to have a shift to the left. Okay, I'm liking this this shorthand. Hopefully you are too. You of course should always know the actual logic. What if we have same errors on both sides? Can you give me an explanation of what your question is here? Oh, same arrows. Oh yeah. So so if you had the same amount of arrows on both sides, like a different chemical reaction. Let's see if the next one. Yeah, so for example, in the next chemical reaction, they don't give us an example, but so say in this chemical reaction here, if you were to, let's say, increase pressure for this reaction, then we would think about it going like one arrow, two arrows, one arrow, two arrows, and then we would stack them together and we would say no effect. No effect. from pressure. Well, you can see that the pressure, the effect here is kind of, going from high to low. We've got one here, and we've got two here. The sort of pressure is the same. So both reaction rates are actually increased, but the amount of change here is going to be equivalent. Hopefully that answers your question. I'm just going to let the video catch up. And so that's a nice little visual explanation for why pressure only has an effect when there is an unequal number of moles on the left and right side of the equation. All right, should we keep going through some of these questions in the worksheet here? I think it might not be a bad idea. So let's do at least one more. So what is the effect on HI if a small amount of hydrogen gas is added? So I like these questions a lot as well because this is sort of more of a chemistry thinking idea. In chemistry, we are not often concerned with every chemical that's in the chemical equation. We know that we can control all the chemicals, and that might be valuable, but we're not. We don't need to. We usually are targeting only the formation of one or two chemicals. So when we realize that we only really care about one or two of these chemicals, then it becomes a little bit of a different question when you go to remove or when you're analyzing these things. So in this example, I might be interested in having some hydrogen iodide, and so to get to that hydrogen iodide, just gonna check. That looks good. Okay. If I'm going to get some hydrogen iodide, then I might only be concerned with what do I have in my lab? How can I modify this? What's the cheapest thing to modify this equation? So here we have our, I'm going to just write it all out again, just so I have a fresh one to work with. Now phases do matter a lot because as we talked about earlier, if it's in the solid or liquid phase, it will not have an effect on equilibrium either. So we do have to watch out if they ever give us anything in those solid and liquid phases. All right, so they are saying that if we added a small amount of HI, then we would be expecting that we've put a little bump over here. Yes, that's correct though. Both left and right. And so we can see that there is now we have a little bump of H2, so the response, so I think of this as this is the stress here, and this is the change, and that change is going to be in a general shift to the left. Shift left, and so that shift left implies an increase in HI. What is the effect on HI if the pressure of the system is increased? So this is the example we just talked about a second ago. So you can see the work above. So see above. Equal moles. So this means that no pressure effect. Pressure cannot change concentrations. Probably concentration distribution or something. What is the effect on HI if the temperature is increased? So this reaction does require temperature, right? So I'm going to duplicate this, bring that down here. Do a little bit of cleanup on it. Just 1 second. That, get rid of this, get rid of that. Okay, put a blue arrow here. Okay, so if we are talking about a increase in temperature, then we are effectively saying we're going to be increasing the amount of temperature here. So that means that we are looking at from the highest point to the lowest point and from the tip to tail. So that means we are looking for a general shift to the right. This also implies that to do this, we also are going to be taking our concentration of HI and we're also going to be going to the right with it. So that HI will start to drop. So we are this shift to the right, shift right, which means that the concentration of HI will decrease. And what is the effect of HI? If a catalyst is added, no effect on equilibrium. Values from a catalyst. Okay, so that's what we did yesterday. I'll try to get those, you know, as I always promise, I'll try to get those answers in as we go. We are going to enter into the most, possibly the most challenging section right away. So I would like to get into that now, and then we'll try to spend a couple of classes on that, or at least 2 classes on that. So this is the big deal here. This is, well, it's not quite, okay, we have predicting, interpreting graphs. Yes. Okay. Yeah. Okay, so we are now at the predicting equilibrium section. So this can be quite a challenging unit to for some students because it does have a high dependence on math. It has we do a lot of mathematical stuff after this point. So we are going to be talking about what is known as a reaction quotient. So the reaction quotient is a temporary value of K. It's not K. It's just a temporary. It might be the same as K, but it's not K. Okay. So the reaction quotient is the measure of the relative amounts of products and reactants present in a reaction at a given time. So for a reversible reaction where A, B, C, and D are the stoichiometric coefficients of the balanced reaction, we calculate Q using the following equation. Q equals C power C times D to the power of D divided by, hopefully you're getting a point right now, A power of A times B to the power of B. So that is that's the equation we're going to be using. This should look really familiar because you have already played around with this equation before. You played around with it before when you called it the KEQ equation. Now this is the KEQ equation if you are at equilibrium. So because Q is a concept that is closely related to the equilibrium constant. Unlike KEQ, which is based on equilibrium concentrations, Q can be calculated whether we are at equilibrium or not. We calculate Q and compare it to KQ to determine if we are at equilibrium. If we are not, if we can determine which direction, if not, I should probably bold that. If not, we can determine which direction the reaction needs to go in order to reach equilibrium. You can think of this as another use of Le Chaltier's principle. So we are looking to, in essence, with Q is a test calculation to see if the system is currently at equilibrium. The value of Q will only equal equilibrium if the system is at equilibrium. Will equal, I want to say, KQ. Any difference? Which direction the system is currently shifting. So this can be a really essential test because in fact systems are very rarely at a perfect equilibrium. They are often in a situation where if you have just mixed two things together, then the chance that they're at a perfect equilibrium is very small unless the reaction is really vigorous. And it can be important to know if you're at equilibrium because you might, if you're not at equilibrium and you're trying to use this reaction for some other purpose, then the concentration of the reactants is still changing. So let's say you create some ammonium hydroxide, and you test. If you don't test it ahead of time, to test its equilibrium, you might still have some of your reactants and some of your products in there that are in a mixed state, and you say, well, this is a reaction vessel of 1 molar ammonium hydroxide, but in fact it might not be 1 molar ammonium hydroxide because it might not have had the time to reach equilibrium if you had just made that reaction, that vessel, and it probably has other extensions as well, where yeah, you might think about. I'm thinking about baking right now, and baking soda is something we add to a lot of baking mixtures. But if you mix your baking soda in, and then if it's a dough or something, and you work the dough too much, the dough starts to lose some of its fluffiness when it's baked. And that's partially because there's an equilibrium being reached for that baking soda where the baking soda will start to degas. It'll start to lose carbon dioxide over time. So if you make your cake mixture and then just leave it, and if you keep working with it, you're actually going to be pushing the baking soda reaction forward, and allowing it to reach an equilibrium that's probably not what you want. You actually don't want the baking soda to react until it's in the oven. So you don't want it to be at equilibrium. You want it to be a little bit before equilibrium so that when it hits the oven and it gets a temperature boost, that baking soda will be active and do things like give your dough a nice fluffy texture. So determine if a system, so this is the skill we want to do, determine if a system is at equilibrium using K and KQ, Q and KQ, and if not, which reaction is favored. So to determine which reaction is favored and in which direction the system is moving, Q is compared to K as in the following. If Q is equal to K, then the system is at equilibrium. The forward and reverse rates are equal and the reaction and product concentrations remain constant. If Q is greater than K, the system is not at equilibrium. And so this means that the numerator is larger than the denominator, should be at equilibrium, i.e., you have an excess of product I have to increase to that point where it matches. Compared to equilibrium. The reaction will shift to the right from this point. Or we should probably say the reaction is currently shifting, is likely shifting to the right. Left. Right? So thinking about it, that we have, remember that we are saying that Q is equal to product over reactant. So if you have K, if Q is larger than K, that means that you have extra product. That extra product will have to be consumed and consumed in order to reach that K balance. This might still be a value that's much, much larger than 1, because K can still be much larger than 1. But if you're even larger than 1, if you're even larger than K, then it means that you must be consuming product. You have gone too far to the right. So if Q is less than K, then the system is not at equilibrium. Here we can say that the denominator is too large. So, i.e., an excess of reactant. The reaction must continue to proceed to the right, forming more product to reach equilibrium. Okay, so let's get some work done here. So for the reaction of nitrogen plus oxygen gives us NO, it was found that 8.5 moles of nitrogen and 11 moles of oxygen and 2.20 moles of nitrogen monoxide were in a 5-liter container. If the equilibrium constant is blah, what are the following conditions at equilibrium? If not, which reaction is favored and which concentrations are increasing, which ones are decreasing? Okay, let's check it out. So we need some things, right? We have, let's write out our equation. We're going to be doing a Q check. Here we are asked about, is it at equilibrium? We are actually given all of the values, right? All the values we need. So are the following concentrations at equilibrium? So we're going to be, that's evidence that you need to do a Q. N2, O2. So we're going to set up our equation like this. Let's get our values out. So we have NO, we have N2. As always, I love it if you can set up a little table of values. Concentration of NO, nitrogen monoxide, in a 5-liter container is 2.20 moles divided by the volume, 5.00 liters. The oxygen is 11.0 divided by moles over 5 liters. And the nitrogen gas is 8.50 moles divided by 5.00 liters. So let's do some calculations. I gotta get my calculator out. I do not want to do that. I want to go here and then pull up a calculator. Great. Okay. You can't see my calculator, but trust me that it's out. 2.2 divided by 5. I'm not doing these in my head. I'm now looking at these values. Okay. 8.5 divided by 5. It's actually, you just multiply by 2, isn't it? 1.70 molarity. And this one will be 22. 11 divided by 5 is 2.2 molar. Okay, don't know if you guys can hear it, but I can hear my 3-year-old having a meltdown upstairs. It's getting a little bit distracting, but that is the joys of working at home. Okay, so let's do this Q calculation. We're just going to punch these numbers in. 0.44 squared divided by 1.70 divided by 2.20. I'm going to get that calculator out again that you can't see. Do not forget the squares. Do not forget how to input values that are in the denominator. So be very careful about those things. And so the value that I got is 0.052 or 518, I guess. 518. We had 3 significant figures throughout, so I can leave it at that. Checking in to make sure nobody's left me any questions. That's okay. This has some sort of equilibrium. This has a value. Notice that in the equilibrium constant that they gave you doesn't even have a value for, or doesn't have units, so we're just going to leave it. So let's compare. So the second stage is compare Q and K, PQ. And so when we compare them, we say that Q is equal, well, let's just go 0.0518, 0.035. So we would say that this value is larger. This is our Q, and this is our KEQ. So we would expect a shift, expect a shift to, let's think about this. We want to shift it so that that number comes down, right? So in order to shift the number down, think about, we want to change. The change we want is down. We need this number to come down. Change needed. And so that means this change is going to be like this. We want this to come down, and we want these numbers to go up. And so that means that we are expecting a shift to the left. We want an increase in reactance, decrease product. And that's that. So that's how you would apply Q. And you can actually do a more extreme question here. There is the next stage of this question that you might do, maybe not with us, but definitely at university you could do this kind of question, which would be to actually take this information and apply it to find the new equilibrium concentrations. So we now know that we're expecting a shift to the left, so we know that we should put the adding x to both sides, or adding x to the reagents, subtracting x from the reactants. So we could think about making an ice chart now. This would be the next steps. Next step, and we would say N2 plus O2. It's been so long that I already forgot how much of this we did. And you've got some values here. You know, you could punch in these values for 4, 1.70, 2.20. We would be looking at subtracting x or 2x from here. We'd be adding x on this side. And all of this, the only reason we know which way to go is because of that equilibrium value. So this would be the next step to do. This is actually a very challenging question because you would have to make that assumption of, you'd have to do some you'd have to do a quadratic essentially, which would not be fun. I feel like we maybe missed a couple of questions on that earlier equilibrium section. Oh well, we'll come back around to that as I make the shorter videos. Okay, so for the following imaginary equilibrium system, we have A, B, and C, and the value of K is blah. If you've got this many and this many in a container and they're allowed to react, after several minutes a sample is taken and it's found that the container contains 1 mole of A. Is the system at equilibrium? Which reaction rate is fastest? Which concentrations are increasing? Okay, these are all very exciting questions. So we have a system that has C cubed divided by A squared and B, and that's going to be equal to our Q because we're doing a test, right? Now, there's some interesting things happen, right? They have said that we initially have, these are initial values, initial, and then we found a current conditions. But we don't know if is current equal to equilibrium? Don't know. Okay, so let's see if we can play with that. So this is this is a really quite an interesting question. Could be quite challenging. So we're going to set up a little chart here because we have an actual change that's happened. Now the interesting thing is that even if you have a change where you don't know if it's equilibrium, and I think I'm gonna have to, I can't really put E for equilibrium. Well, maybe I'll put like an E with a question mark. So that's my current conditions. So they're saying that after a while we have 1 mole per liter. It's only 1 liter container, so 1 mole per liter. And initially we had 1.5 moles per liter. We didn't have any C. We're going to make that assumption. And we have 3.20 moles per liter of B. So the change that we've seen here would have to be minus 2x. We have to watch out because there is a 2 in front. So this one is minus 2x minus x, and we get plus 3x. So the total change that we've seen between the initial and the current conditions is a change of 0.5. So we had 1.5 minus 2x has given us 1 molar. This means that x must be 0.25. So minus 0.5. So that means that this is minus 0.25, and this is plus 0.75. Because there are 3 of those x's there. So this change leaves us with 2.95 here. And we have over here, we have 0.75. And so now that we're going to take these concentrations and we're going to pump them into this equation. So 0.75 to the power of 3 divided by 1, 1.0 to the power of 2 times 2.95 to the power of 1. And we're going to do a little test, see what that is equal to. So let me do some math. 0.75 to the power of 3 divided by, the 1 doesn't matter, so 2.95. Okay, so I get 0.143. Well, 0.143 compared with K 0.22. So K is equal to 0.22. Oops. 2. And Q is equal to 0.143. Q is less than K, so this equals a shift to the, where we need to go, Q needs to go up, right? So if Q needs to go up, that means we have to bring this up and this down. So that means we're going to be producing more product. More product is a shift to the right. Need more product. Okay, so is the system at equilibrium? No. Which reaction rate is fastest? So this, this one's no. Okay, so which reaction rate is the fastest? This is cool. I like this question a lot. At this point, you have an excess of your reactant. More concentration equals more speed. So the forward reaction is faster. And which concentrations are increasing? The product is increasing. Okay. How many more examples? Oh, we got one more example. Okay, we can definitely do one more example before we run out of time here today. So for the example 3, we have a K of 49. We have some equation. We have a bunch of stuff in a 2-liter container. Boy, I hate when they do that. Put that extra volume. Which way will the reaction shift in order to reach equilibrium? Okay, so let's get it all set up here. I like to have a nice big equation to work with, so I'm going to write it all out. NO plus O2 gives us 2NO2. And I'm going to write out my concentrations of all my things. And I've got, so for NO, I have 2 moles in 2 liters. 2.0 moles in 2 liters equals 1 mole per liter. In O2, I have 0.20 moles in 2.0 liters. So that gives me 0.10 liters. And I can hear one of you at home going like, hey, don't get rid of your sig figs. You're right. 0.40 moles divided by 2.0 liters. And that gives me 0.20 molarity. And that one's an L, which is supposed to be an M. So I'll punch those into my equation, which I didn't write out, so I better write that out. And that's going to be equal to Q in this case, because we don't know if these are equilibrium or if they're not. So let's put the NO2 is on top, 0.20, power of 2. We've got 1.0 down here to the power of 2, and we have 0.10 to the power of 1. Okay, so it's going to be 2 points, or it's going to be 2 something. 0.2 to the power of 2 divided by 1 squared times 0.1. Okay, so I got 0.40 is equal to K. So if we compare that to our K, so Q equals 0.40, K equals 49. Which way is it going to shift? Well, we have not even started this chemical reaction, right? So this reaction is too small, so we need to pump up this value. So to get that value to go up, we need to bring up the products and bring down the reactants. So we need a shift to the right. And well, there we go. So that's it. Okay, so have fun with that. There's a bunch of questions you can do after this, and I'm going to let you go for today. And I will try to get back at it this afternoon and start working on the earlier videos, making some condensed ones to go through some of those practice questions, because I'm thinking that we have some missing videos later. And then I believe there is one last lesson at the end here, right? Interpreting graphs. Yeah, so that'll be tomorrow's lesson, and we'll be done equilibrium, and I'll get you some assignments out there. All right, have a good day. Best of luck. Stay safe, and have a good one.